All right, today we're going to dive into one of the most famous, and let's be honest, most mind-bending rules in all of physics, the uncertainty principle. It's an idea that really messes with our basic gut feelings about how the world is supposed to work.
So let me just ask you something. If you had the absolute best, most perfect tools imaginable, could you know everything about an object at the very same instant? I mean, its exact location, its precise speed, the whole shebang. Our intuition screams, yeah, of course. But you know what? The universe has a very different answer, and it's a hard no.
And this really gets to the heart of it. On one side, you've got the world we think we live in, the classical dream. You know, the idea that if we just build better tools, we can get better and better measurements, forever. But on the other side, there's quantum reality. And it tells us, nope, sorry, there is a fundamental built-in speed limit on what we're allowed to know.
So, to really get a handle on this hidden rule, we first have to understand the world we thought we lived in, the world of classical physics.
I mean, think about a baseball flying through the air. With a good enough camera, you could totally figure out its exact position and its exact speed at the exact same time, right? That's classical physics for you, the physics of Isaac Newton. It works beautifully for baseballs, for planets, for pretty much everything we see in our daily life.
But here's the thing. When you zoom way, way down to the tiny world of atoms and electrons, all that common sense just evaporates. Quantum mechanics comes along and says that our everyday assumption isn't just a little bit off, it's completely, totally wrong. And the guy who gave us the key to this bizarre new reality was Werner Heisenberg.
Okay, so let's go back to 1927. A brilliant young physicist, Heisenberg, comes along and drops an idea on the world that basically turns our understanding of everything upside down.
He basically said that some things in the universe just come in pairs. Physicists call them conjugate variables. The famous one is position and momentum. And these pairs are locked in a kind of cosmic seesaw. The rule is shockingly simple. The more you know about one, the less you're allowed to know about the other. It's a trade-off.
And this unbreakable cosmic law, this fundamental speed limit on knowledge, well, it's got a name you've almost definitely heard before. The Heisenberg Uncertainty Principle.
Now, whoa, don't let the math scare you. This is actually pretty simple. All this equation is saying is that the uncertainty in position times the uncertainty in momentum can never be zero. So if you squeeze the position uncertainty down to almost nothing, the momentum uncertainty has to balloon up to keep the universe balanced. It's not a suggestion, it's a law. Okay, so that's the rule. But why? I mean, why is the universe built this way? It feels so weird, right? Well, there are a couple of ways to wrap your head around it, and the first one is a little more intuitive.
It boils down to this. You can't just be a passive bystander in the quantum world. The very act of looking at something, of measuring it, fundamentally changes it. You're not just watching the show, you're part of the action.
Let's just walk through it. Say you want to find an electron. To see it, you have to bounce something off of it, usually a photon of light. Now, to get a really precise location, you need a powerful, high-energy photon. But here's the kicker. That powerful photon basically acts like a cannonball, slamming into the electron and sending it flying. So congratulations, you knew exactly where it was, but now you have absolutely no idea where it's going. Now, that's a great way to start thinking about it, but it's not the whole story. Not even close. It kind of implies the particle had a definite spot and we just messed it up. The truth is much, much weirder. The uncertainty isn't something we cause. It's baked right into what the particle is. And here we go. This is the absolute core of it all. At this super tiny level, an electron isn't just a little ball. It's also a wave. At the same time, I know, it sounds crazy, but this wave-particle duality is the key. It's where reality starts to get really, really strange. So look at what this means. If you have a nice, long, spread-out wave, you know its wavelength and therefore its momentum perfectly. But where is the particle? Well, it's kind of everywhere along that wave at once. Your position is a complete mystery. Okay, so what if you want to nail down the position? You got to squish that wave into a sharp little spike. Great, now you know where it is. But to build that sharp spike, you had to mash together a ton of different waves with all sorts of different wavelengths. And since wavelength is momentum, your momentum is now a total mess. You see? You just can't have both at the same time. It's built into the very nature of being a wave.
And you know what's wild? This isn't just some abstract quantum thing. Engineers deal with this exact same problem every single day. If you want to create a really short, sharp pulse of sound, a little blip in time, you have to use a huge wide range of frequencies to create it. It's the same exact trade-off. A precise spot in space needs a messy range of momenta. A precise moment in time needs a messy range of frequencies. It's just a fundamental property of how waves work, period.
So right about now, you might be thinking, okay, this is a fascinating, weird fact, but so what? Does this actually matter in the real world? And the answer is a huge, emphatic yes. This principle isn't just theory. It literally powers our entire modern world.
I mean, this fuzziness is the only reason atoms are stable. If an electron could just sit still with zero momentum, it would instantly spiral into the nucleus. Uncertainty forces it to stay in motion. It's also the secret behind quantum tunneling, where an electron's fuzzy position lets it pop through barriers it shouldn't be able to cross. That's a trick that's essential for the flash memory in your phone. Seriously, from computer chips to quantum cryptography, our world is quite literally built on a foundation of uncertainty.
So, let's bring it all home. What's the one crucial thing you should take away from all this?
It's this. The uncertainty principle is not a bug. It's a feature. It's not about us having clumsy tools or not being smart enough. We can't just invent a better microscope and make this go away. This is a fundamental, non-negotiable rule of how the universe is put together.
It means that reality, at its very core, is inherently fuzzy. There's a limit to how sharp the picture can get. The universe has secrets that it will never give up. Not because we're not clever enough to find them, but because there's simply no answer there to be found in the first place.
And that kind of leaves us with one last big question to chew on. If our most basic common sense idea about knowing things turned out to be totally wrong, what other obvious truths about our world are just sitting there, waiting for us to realize we've had it all wrong? What else don't we know that we don't even know we don't know?